Thank you. I'm also very pleased to be here. Hidden behind these interdependent hitting times is an actual dynamic structural model with strategic interactions, so don't worry. So the motivation for working on this is an observation that you often see people doing things at the same time, synchronization, and there's multiple mechanisms that could lead to that. One that's very interesting is complementarities. The fact that your payoff from doing something may increase if someone else does it as well. Another may be sorting on characteristics. Maybe you just hang out with people who want to do things at the same time as you. Could be. Could also be common shocks. You just together with your partner hit at the same time with some shock that makes you do something together, but not because there's a causal relationship or a particular relationship between what the other person does on your payoffs from doing the same thing. And there's quite a few examples in the literature. For instance, by Honoré and Aurora de Paula, they in the specific, I mean, many people, of course, study retirement of couples, but they do that in a duration context. And the idea is that if your spouse retires, that may change your payoff from retiring, maybe up or down, I don't know. But if it makes it more attractive to retire as well, to do things together, then we lead to synchronization. Aurora de Paula's job market paper, I believe, studied this problem. And he focused on an application was desertion from the Union Army in the US Civil War. And there, it's clear that there may be complementarities to flee your company, may be more attractive if the people you leave behind flee with you, right? Because otherwise they may, become agitated and shoot you. So that's one reason why there may be complementarities, or why there may be synchronization. But it could, of course, also be that these companies are, people, all the cowards sort into one company. I don't think that's actually very likely, but that would also lead to some synchronization. But of course, what could happen in a war is common shocks, right? You're bomb sheltered with your company and you all flee. And again, you get synchronization. And there's many examples like this. So for instance, in the literature on risky behavior, there's these peer effects that you could see as complementarities. Because the other reasons why kids do things together. Things like bank runs. An example that I will use as a leading example here is retail entry and exit. It may sound like an example where there are no complementarities, but strategic substitutes. But I'll come back to that. There's actually a story here. There's not an actual example in this paper, just in case you were wondering. This is again back to econometrics. Now, why is this interesting to study this in a bit more detail? Because we know from, for instance, Mansky's work that these three mechanisms that may underlie dependent behavior, synchronization, typically have come with different distinct policy implications, right? And so that's why I want to look into that a bit more. So what do I do in this paper? I will discuss the specification, identification, estimation, so the econometrics of models of multiple durations. So this could be the durations until desertion or until exit from a market, where these durations are the outcomes, specified as the outcomes of stopping games in which these three mechanisms play a role, are explicitly modeled. One would be common shocks. So in each game, there's a process that could be a Brownian motion or something that's slightly more general. I will focus on spectrally negative Levy processes. Those are the Levy processes with only negative shocks. Now, that sounds a bit specific. Just think of it as being more general than Brownian motion, and then it's all good. That turns out to be really useful to make that restriction. It has observed and unobserved player characteristics that may embody this sorting effects. For instance, that cowards all sort in the same military company. And it also has these complementarities because payoffs in this game may depend positively on what other agents do. So if other agents exit, it becomes more attractive for you to exit as well. And if you could identify and estimate such a game in a particular application, there you could make a distinction between those three mechanisms, right? And the main idea of the paper is that a very, in theory, very standard class of such games, often called, reoption stopping games in the more theoretical literature. So these kind of games driven by Brownian motion or more general level processes, reduced to econometric models of interdependent hitting times. So the reduced form is a specific class of duration models where each duration until something occurs is a hitting time, a time that the underlying process that models the common shocks hits a threshold, and where the thresholds are heterogeneous and moreover may depend on the state, so where the other agents are already left. And that actually connects this analysis of games to more, slightly less structural work on this class of duration models. And that also means that I can use results from that other work to actually establish identification and develop estimators for this kind of these kind of games. Now, a bit of background before I start with the actual model. So there's a smallish literature on the econometrics of continuous time stopping games. Of course, there's a whole literature on games, econometrics of games, in particular the last 1 or 2 decades. But there's a small literature on stopping games that are modeled more in a duration-like context. I already mentioned Areo's job market paper in the Journal of Econometrics. So that actually is also a stopping game where payoffs are driven by Brownian motions. But the key difference with the model I have here is that there's agent-specific Brownian motions leading to agent-specific processes for their payoffs, and that these are privately observed. That leads to all kinds of complications that I think explain why I can come up with stronger identification results and simpler analysis than Areo could in his paper. Then there's 2 papers by Bo Honoré and Areo. The 2010 paper, that's actually called Interdependent Durations, which kind of motivates this title. That's a complete information game, and my game will also be a complete information game. But the key distinction is that in their game, the path of payoffs is basically deterministic. So there's no ongoing uncertainty. There's not this kind of option values that you have in this more standard Brownian motion-driven reoption style games that I study. And they do that, they basically design that game so that the reduced form is a multivariate extension of a well-known class of transformation models, the generalized accelerated further time model that Git Ridder studied, which, in their case as well means that they can actually use results from that literature to analyze their model. And so that's very similar to what I do, of course. I connect these class of models that I study to the duration literature as well, but in a different way. 2018 paper is the paper on retirement. That actually is the first paper is a non-cooperative game. That's actually that's cooperative decision making on retirement in that game. And the Lin and Liu paper is a paper where that's very much like the 2010 paper that has incomplete information. It also relates to the literature on. Should of course not point on this screen because you probably won't see that unless you have a very clairvoyant. Duration analysis, in some sense, it's related to this paper that I had with Gerard Vandenberg, where we study it's called treatment effects in duration analysis or something like that. And that's a hazard. It's not a structural model or anything, but it's an analysis of the effects of one event on another event, where you both allow for a direct causal effect, a treatment effect, but also for correlated and observables in both hazard rates. And we discussed the identification of that, and we also have some applications in other papers. So that's a theme in the duration literature to actually, explain what determines the relation between events that you observe in data and to distinguish causal effects and selection effects in this dynamic setting. And in some sense, of course, we do the same here, right? But now we more explicitly model the structurally model the interactions, and so it's a bit different. I'm using many results from this 2012 paper that actually studies the identification of hitting time models where the durations are specified as the first times Levy processes hit heterogeneous thresholds. So those are models that you can actually use to model single agent optimal stopping problems. We basically extend that. Basically, the main point of this paper is you can extend that to a multivariate setting in which there's strategic interactions. There's a theory, there's a large literature on these reoption style optimal stopping models, optimal investment timing models. Of course, it goes back way earlier than these books and papers. But in these papers in particular, so the Boyashenko and Lewisdorfsky book has developed this for Levy processes, which is kind of convenient for my paper. So we use that a lot. I'm using the Simon and Stinchcomb paper to motivate, to deal with some formalities of games in continuous time. And for instance, Murto is an example of a paper where actually a game is developed, an optimal stopping game. In that case, a war of attrition, so a game that doesn't have complementarities but strategic substitutes. But we take also inspiration from that. Then in terms of using continuous time models to simplify things, because in some sense that's what I'm doing here. There's also some work by, for instance, Dorochelski and Judd and Archidiakono and co-authors who take the more standard dynamic discrete choice models and games that we have seen already today, right? But actually have choices being taken at Poisson times or at random times. And that's very convenient because in their case, it simplifies things, because if multiple agents take decisions at their own Poisson times, they never take decisions together. So you avoid simultaneous decision making, and that simplifies things and simplifies computations. So that's different from what we are doing, because even though Poisson processes play a role in compound Poisson processes, for instance, are Levy processes. A key distinction is that we focus on payoffs that are driven by these persistent processes like Brownian motions, where you get these option value considerations and all that. And they just use this as a, they don't have this persistence through this process, and so it's a completely different class of models. I will mostly discuss this based on a simple example that I won't actually implement. So, but I'm just like to use some real words instead of just only abstract words. And I will not give the general model and development. Just try to give some intuition. So the example is one of a shopping mall with two anchor stores called A and B. It's not a completely ridiculous example because I took it from a paper in, I believe, marketing by Anna Vitorino, who studied whether anchor stores, so key stores, you have these strip malls in the US, so I've heard, and important shops in these malls, you may call them anchor stores, actually are the bigger stores that are there, among other things, to actually attract customers to the mall, and that benefits other stores in the mall, and that benefits also each other. So she studied whether these stores actually complement each other or substitutes, and she, of course, allows for both, and she finds that by and large the complementarities dominate. And so it's not so strange to think of this as a game with complementarities. And so I basically studied the problem, what if you have a mall with two of these anchor stores that complement each other, so they really need the presence of the other store to generate maybe enough consumer traffic or to somehow make it feasible to be in the mall, right? And with that mall, it may be a dwindling, mall, demographics may go down, and at some point, one or both may leave, right? So how would you model that? Well, both stores continue in this. So I model it as a game. Both stores contemplate exit. It's an infinite horizon game. As long as both are active, they decide to exit simultaneously, right? So simultaneous decision making continuously over time. This is a bit weird, the second bullet point here. As soon as one store exits the mall, store J can respond immediately. It's of course not completely obvious what that means in continuous time. That's why I use the Simon and Sinscombe paper. So we try to be quite careful about that in the paper. But just for now, accept this. If J doesn't, the other store doesn't exit at the same time, it can leave at any future time, right? So it stays in the mall alone, and then, you know, the other store will never come back. It's absorbing and it's gone. So how do we specify payoffs in this example? Well, the payoffs depend on whether, and I use the J and the L for joint and loan to denote the state dependence, the dependence on whether the other store is still around. And so the payoffs depend on that, on J or on L. They also depend potentially on store identity, on I, but there may be full, heterogeneity. And so what are the payoffs? Well, if you're still in the market together, in the mall together, then, so if you're a joint anchor, if I is a joint anchor, it gets some revenue, RI sub J, super J, minus some cost, CI super J, and then some, increasing function, X gamma I of some mall-specific process YT. So this may be a Brownian motion or something else. So that's the thing that's moving the mall around, and at some point may lead to the firms leaving, right? If it goes up too much, it gets too costly. Once you are a loan anchor, so once you are alone, you get a similar payoffs, but with parameters that have an L on them. So there's state dependence there. There's dependence on what the other agents does. That's of course where you want the complementarities to come in, and that's modeled through the revenues from being in a market jointly being larger and the costs being smaller, both weekly, but so potentially doesn't matter. That's the complementarity. The gamma I is a positive parameter. In this example, the YT is a Brownian motion. It's a mall level thing, so it's common to both firms in the mall. And that's positive parameters. It's a complete information game. So at each point in time t, so both firms know all the parameters, the payoff parameters, and also know the entire history of the game. There's no private information. And I focus on pure Markov strategies. So a store leaves the mall whenever the latent process, the mall state YT, hits some set of Y's that's specific to the state. So whether the other firm is still around or not, and maybe individual specific if the agents are different, okay? And in fact, these exit sets will be, I will take those to be threshold sets, so they will leave as soon as Y is too high, right? Because if it's high, the cost is high, and the payoffs from staying are low, all right? So these categorized Y's will just be threshold sets. So sets of Y's above a certain level, the threshold. So this is the setup. Yes. Say that again in the last.
There's a simultaneous movement.
Yeah.
And when you say Markov, I'm trying to figure out, do I know what the other guy does this period?
No, because it's continuous time, right? So you know everything up to you know the state, but you know all the survival histories up to, but not including this time. Yes.
But isn't the answer yes? Because you said that the firm can respond
Well,
immediately.
yeah. Well, the answer is yes and no, I guess. You're both right. I mean, I try to stay friends with everyone, right? Excellent, both good. No, it's that's the subtlety in the second main bullet point, the 3 bullet points below that. So as long as I guess Ariel was asking about what happened if they are still both active in this site simultaneously. At that point, they don't. Of course, it's a simultaneous move at that point, right? But as soon as one moves, the other gets another opportunity to respond. And you can actually formalize that using a discrete time approximation. That's the Simon and Stinchcomb thing. If you would write it down in discrete time, there would be an additional, node in the tree, so that you can have the problem with the continuous time is you cannot have immediate responses if you don't model it explicitly. And so we model that explicitly. So it's a bit subtle. Now, so I will analyze the equilibrium of this game. So the agents choose, the equilibrium is a Markov perfect equilibrium. So the agents choose pure Markov strategies that maximize expected discounted payoffs, where the discount rate should be high enough to ensure that expected discounted values exist, expected discounted payoffs exist, and they play Markov perfect equilibrium. So there's a bit of subtlety there. So the discount rate can in principle be firm specific. It should be larger than this this thing that you recognize, I guess. The gamma comes from the fact that the the payoffs depend on exp gamma y. That's why there's a gamma there. So the real process you care about is gamma times a Brownian motion. So that's why that's there. This basically ensures that discounting is enough to compensate the expected growth in the cost, so that you get finite expectations. I introduced some notation secretly here. The psi that will actually pop up later, actually at the bottom of the same slide, so not that much later. So the the psi function actually is the plus function that characterizes the Brownian motion, as you can see, right? So it's clearly, if you know that function, you know which Brownian motion you have. I introduced that explicitly because I need, it needed later on, and it also plays a role in the extension to Levy processes. So I'm not trying to be fancy with notation here, and I'm actually going to use that. Now, so how do I solve this equilibrium? You can do backward recursion, of course, because once one of the firms is gone, then you basically have a single agent problem. This is a very standard optimal stopping problem. In this case, based on a Brownian motion, you can just go to Nancy Stokey's book and see what the solution is. Now, I don't believe my particular version here is in her book, but that doesn't mean it's not a standard problem. And this is how it works. So I have an explicit solution here. That's why I have this simple example. What is the optimal behavior, the optimal strategy prescribing in this what I call the lone anchor subgame? So the lone player subgame, right, where you are alone. So from I is alone, from I will leave whenever yt is above a certain threshold, the threshold y bar il, the L for lone, the I for player I. It has this functional form, and it has a lot of, no, it works. So the gamma, of course, because really what you care about is gamma times y, right? So that's why the gamma is there. I have that there not to be fancy, but just because that's one of the things you could make heterogeneous. You get a particular functional form for the thresholds out. So it's kind of useful if you go to the econometrics. The log is there because there's the exp. It's just a ratio of, well, you know what that is. So I have to explain what this is. So lambda is this. Again, it depends only on the Brownian motion that drives payoffs here. This is just following from this, okay? So this is something that we know. So we know this is positive, this is positive. It's actually defined as the positive root of this polynomial, this parabola, minus rho, so where it's equal to rho, or it's essentially its inverse on that, evaluated at rho, where it is invertible, so on the upward sloping part. That's not so important. This is really what it is. Why do I have this here? Because lambda, like psi, characterizes the Brownian motion. If you know this guy, you know which Brownian motion you have, which is useful to know for the identification analysis. And this lambda also plays a role in the implied duration model, because lambda is characterizes the first precise time process, and so it pops up in the expressions later for that characterize the distribution of the first precise times. Okay, and again, just like the psi generalizes in the Levy case, this also generalizes, and basically this equation that we have here for the Brownian motion case in this example directly applies to the more general case. It's just that the psi and the lambda will have different functional forms. We'll not only have a mu and a sigma, but also a non-parametric component, which, you know, captures the rest of the Levy process, the shock part. So for some things about this. So one thing you can show is that if rho goes to infinity, first of all, this is always larger than this part is larger or equal to 1. It goes to 1 if rho goes to infinity. So if you're very impatient, if you're myopic, then you will leave as soon as the x to the power gamma y is equal to c over r, or whenever the current payoff is below 0, okay? Which is exactly what you would expect, right? If rho is finite, this will be larger than 1, and so you will actually be a bit tolerant to negative current, current negative profits, which is because of the upward potential, right? The option value. So that's all in here, and other things make sense as well. If C is larger, costs are higher, you have a higher threshold. If costs are higher, you have a higher threshold. That actually it may actually be the wrong way around, I guess. If these guys are the wrong way around, so that's kind of unfortunate. If I just changed this last night. If the from another example, if the revenues are higher, so if R is higher, then of course you tolerate higher cost, and so you would have a higher threshold. If the C is higher, then you have higher cost, and you would only tolerate a lower Y. So we know what happens in this subgame, right? So what when they're still joined? Well, it turns out you can actually solve for the Markov perfect equilibria by considering an auxiliary problem, which is the problem that an agent would solve if she would always get the joint payoffs, right? This is also, again, a single agent problem. The solution to that, of course, is the same. Well, except that, you know, well, it's the same, but it should also be corrected in the same way. So a single agent that would always get the joint payoffs basically uses the same threshold rule as the loan mole, but the loan store, but it would use it with a threshold that depends on the parameters for the joint payoffs, right? And it turns out that there's two classes of MPE that can be characterized in terms of the implied outcomes, one in which there's sequential exit and one in which there's simultaneous exit. And so we use this notation, the max and the min of the max of YL, which is the max of the loan thresholds, and the min of the Y bar J, which is the minimum of the joint threshold across the two players. And these two cases I discuss in with some graphs here. So if the maximum of the loan thresholds is larger than the minimum of the joint thresholds, now given that the joint threshold for an agent is always above the loan threshold, because, you know, if you get higher payouts because of the complementarity, you want to, you know, you tolerate higher cost, right? This means that heterogeneity is so important that one agent has even a loan threshold that's above your joint threshold, right? That means that heterogeneity is really big relative to the complementarities. That's also reflected in this graph. So, you know, one example of that is what is said there. So, for this agent I could be the low payoff agent. So that agent will leave relatively quickly. Both his loan and the joint threshold are relatively low. Agent J is the agent with the high revenues or the low cost parameter. So that agent will have very high thresholds, both in the loan and the joint case. So independent of what the other guy does, very high thresholds. So the top two thresholds here, these are the threshold, the red and the green. The green are the joint threshold, the red are the loan thresholds. The solid ones are the ones that are relevant for the story. The other ones are the other ones. There are four, right? There's two players. There's two states. The top two thresholds are the thresholds for firm J in this example. So the bottom one of the two is a loan threshold, the top one, the joint threshold. And so clearly the thresholds for the high profit firm are both above the true thresholds for the low profit firm, right? So it means lots of heterogeneity. The heterogeneity is reflected by the difference between the top two thresholds and the bottom two thresholds, and relatively little complementarity. Complementarity is basically reflected by the difference within a firm between the green and the red thresholds, right? And so in this case, what you get is a sequential exit, because whenever so what's on the what's plotted here is time, right, on the horizontal axis. On the vertical axis, there's y, values of y. One realization of the mole specific Brownian motion is plotted here, and essentially what this means is that firm J, the top firm, will whenever y is below this max y bar L, will not find it profitable to leave whatever the other guy does, right? So it's dominant to actually stay. That means intuitively that for the bottom guy, the guy with the guy I with the low payoffs, that guy never wants to stay above min yj, because that's the maximum. That's the what he would get if the other firm is always around. He always gets the complementarities, and so whenever that firm is around, the other firm will also be around, and so that firm will basically leave at T1 when y first hits the threshold min yj, which is a joint threshold for the low profit firm. And then once that firm is gone, of course, the second firm, the high profit firm, will leave when y hits the solid red threshold, which is the loan threshold for the high profit firm, right? So in this case, because heterogeneity is really important relative to complementarities, there will be sequential exits. They're so far apart that the worst firm will just leave first and the better firm will leave second, and the complementarity is not large enough to override that. Now, in this case, you actually do have multiple equilibria. And this, for instance, has to do with the fact that in this setup where you can actually respond to what a firm does, in some states it doesn't really matter what you specify the strategy to be. So the strategy is not always relevant in the response node. As you can get all kind of multiplicity here, but in this particular case, when the parameters are such that that this inequality holds, there's a unique outcome in Markov perfect equilibrium. That's not true in the other case. This is the case where complementarity dominates heterogeneity, and in which you get synchronization. In this case, you have multiple equilibria that actually also have multiple outcomes. So stores may fail to coordinate on the best outcome. And the only thing we know is that they actually jointly, when y hits some threshold between that max and that min, right? So in this case, you see that the joint thresholds are both here. This is the joint threshold for one of the firms, this is the joint threshold for the other firm, and both loan thresholds are here. So now the thresholds for the two firms overlap. So the heterogeneity is not very big, but the complementarities are very big, right? Because the distance between them is big. So now you can argue that they will both leave. The best scenario for both of them is that they both decide to adopt the threshold, that their strategy is. And if they do that, if the other firm does that, you don't want to deviate. You don't want to stay longer. Or at least one of the firms doesn't want to stay longer, right? Because even if the other firm would always stay around, that would not be profitable. But you also don't want to deviate by not staying if the other firm stays. But you can actually make that argument for any point in between here, up to this point. Below here, of course, for one of the firms, below here it would be never be good for one of the firms to leave. So anyway, so between these 2 points, you can create a whole range of equilibria. We will basically select the one that's the most efficient, which is the one where they somehow manage to coordinate on staying in on the highest threshold. You can also develop what we do here more generally, but then you would have an additional source of heterogeneity, which is the equilibrium selection of some threshold in this interval. So we don't do that. We just pick the best one, the efficient one. That's something you could do. Now, we generalize this in the paper. We improve this in the paper more formally for a general game. So we don't need this particular payoff structure. We just need general payoffs that are decreasing or at least monotone in YT to get this threshold structure, and that have this complementarity feature. And we allow more generally for spectrally negative Levy processes. So this is a more general semi-parametric class of processes YT. And this model that we study in the paper actually includes a simple example as a special case. For instance, you can directly extend the simple example to Levy-driven payoffs. Essentially, you get the same analysis, except that the lambda and the psi that we had before, were just functions parameterized by mu and sigma, right, are now parameterized by mu and sigma and some non-parametric measure that characterizes the jump part of the Levy process, right? So just more general, but the analysis just continues. Now we also, analyze games with more than 2 players. So actually, the analysis continues as before. So you have a similar model with a similar type of complementarity. So if there's say 5 players, you just have 5 utilities for each player. So we assume that the complementarities only depend, or the interactions only depend on the number of players you're around with. You could generalize that, of course, more broadly to depending on the identities of the other players around. We don't do that. So there's general heterogeneity in the utilities, but it only depends on the state of the game, on the number of via the number of survivors, and then this actually imposes the complementarities. Now, if you do that, it turns out you can actually fully characterize the duration outcomes in a similar way as I did before, using again a set of thresholds, one set for each player and one threshold for each state the player can be in. So each number of firms the player can end up with. Now that's on the next slide. I'm going to, I guess, skip that. I have 15 minutes?
Yeah, about 13 minutes.
30 minutes, okay. Forget this, just focus on the top 2 lines so I don't completely so how do the duration outcomes that are implied by this model work in this case? Well, basically exit occurs in a number of waves. The maximum number of waves is the number of players in the game, right? Because there can only be so many exits in a game with I players. And in each of these waves, one or more agents simultaneously exit at a hitting time of the type that we have seen before. So the minimum of the joint of the hitting times correspond to that number of players. Now you have to be a bit careful to actually, this basically gives you an algorithm to how to calculate those waves. This is an algorithm that, for instance, we use in simulating data from this model. So how does this work in the 2-player example that we've seen before? Well, in the sequential exit case, you basically have 2 waves, right? In the first wave, the first firm exits. In the second wave, the second firm, right? And why is there why is there only one firm in the first wave? We know why there's only one firm in the second wave, because only one firm left. Well, because after the first firm leaves, he leaves the other firm behind alone. But in the parameter values that we have there, it's not profitable for the other firm to follow and also leave, right? But that is generally not true, of course, and we have seen in the 2-player case, it's not true when there's simultaneous exit. There, once one firm leaves, the other firm, because of the loss of the complementarity, also leaves. So the wave there takes 2 firms out. This is basically a recursive algorithm that computes that. So you could, for instance, have a generalization where there's 9 firms that are very similar and very profitable, and one firm that is way worse, right? And there's moderate complementarities. They would have a first wave where the first firm leaves at some point. Then if you check, you will see that the other firms don't want to leave. But then you go to a second wave, if the Y is higher, then when y hits a next threshold, which you can again characterize as I did before, especially in terms of the model primitives, at that threshold, as soon as one firm leaves, all the other firms want to leave as well because of the complementarities and because they're very similar. So you get a generalization of this idea that we had for the two-player game, and that you can use to model this. Now, how do we take this to data? We basically assume that we have, so we use this results that I have in this this earlier paper, and we assume that we have a sample of games, say a sample of moles, right? With data for the two-player case on both durations, where of course the two durations could be the same if there's synchronization. Possibly we observe the identity, so who is the first to leave, who's the second to leave, which is useful if you have data on the covariates on the players, on the firms in the market, right? And we have potentially covariates for each game. So we assume that these markets are independent, and that the outcomes in each market are equilibrium outcomes from the type of game that we have, driven by, in general, especially negative Levy process, and in which all the primitives in the threshold may vary across agents, which was explicit in the subscript I, but only through the covariates and through a vector of two observables, VA and VB, one for player A and one for player B. And of course, we will not be able to identify all these things, not even if we put the C and the R in the right order, because, for instance, we could alternatively have CI being heterogeneous or RI being heterogeneous. It would lead to the same reduced form, right? The same decision rules, same variation in the decision rules. So we focus on certain reduced forms, and then in the second stage, we wonder about how you can learn from those, once you have identified those reduced forms, how you can learn about the underlying structure. And we focus on two main classes of reduced forms, a multiplicative one and an additive one. So one that is multiplicative in the effect of the state, so how many firms are still surviving, one or two, and the covariates that you observe, and the unobservable, and one that's additive in these two things, right? Where we also assume in that case that the unobservables are independent of everything else, and that also everything is independent of the latent process. So the latent process is not related to X and V. Now you can easily see, if you see our particular example here, which is one example, that you could easily generate a reduced form like that, right? For instance, if you make C or R, or C over R, or R over C, if you make that a multiplicative function of X and V, then the threshold will be this additive form, right? And so you can imagine that there's other solutions to this model where you can get the multiplicative form. You can even get that here with a bit more contrived modeling. And so we use that. I want to note that, so we use that functional form, those reduced forms, to discuss the identification. And then in the second stage, you can go back to the structural form of Y and see where from the reduced form you can get the structural parameters. I want to note that if you have group data, so if you know that certain moles have the same V's, you can use these kind of panel techniques and you don't need any of this structure, right? So you can allow for general effects of X and general dependence with X. And so we have both results in the paper. So how is this an econometric model? Well, this just takes one of the examples again of sequential exits, right? Now, one source of variation, econometric, sample variation that you will have is that in different markets, we'll see a different realization of the latent process, right? So markets that are the same in terms of the V's and the X's, so have the same reduced form, the same thresholds, will have different durations because there's variation in the Y, right, between markets. So that's one source of variation. Another source of variation, of course, is that different markets will have different V's and different X's, and therefore different reduced forms, different decision rules, and different equilibria. And so this market may have this equilibrium, right? Another market with sequential exits, another market may have this equilibrium, right, with simultaneous exits. So those are the two variations, and that's how this is leading to a interdependent hitting time model, right? The durations are hitting times. They're interdependent through, well, on the one hand, the complementarities, but also because of correlated unobservables. And this is how this is now a interdependent duration model derived from the game. So for identification, I'm not going to go into detail, but we basically, once we have made a step from these optimal stopping games to one of those interdependent hitting time models, where you basically have a duration model where all durations are the hitting time of a Brownian motion or something like it, to an heterogeneous threshold, you're in the world of that earlier paper where I discussed that for the univariate case. And I can basically leverage all the results that I have there in this setting. And in particular, for instance, if you paid attention, or if you're not, I will tell you, the first exit in all cases takes place when Y hits one particular threshold, namely the minimum of the joint thresholds, right? It's true that in one case that's only the first firm exiting, and in the other case that's both firm exiting. But it is true that the first exit that you observe is always the time that the Y hits that minimum of the joint thresholds. And so the structure of that is exactly the structure that I've studied before. And so the results for the univariate case immediately apply to that. There's one complication, of course, is that the threshold is not directly related to the primitives, but it's the minimum of two thresholds that is related to the primitives, right? There's an additional complication there that comes with the game, but you can easily see how you immediately can apply those single spell results. So that's basically what we do, and we use this particular characterization. So one way of characterizing the first time a Levy process hits a particular threshold, the threshold is this phi x times v or phi x plus v, right? Is through its Laplace transform. There's a one-to-one relation with that. And one key trick in that earlier paper is that we know that there's from the literature on Levy processes, that we know the functional form for that explicitly. So we don't know what the distribution is, right? But we know what the Laplace transform of the distribution is. And it can be expressed in terms of the threshold y and in terms of that lambda function that we have seen before, which is why I had it before. So this is a key equation from that earlier paper that we use a lot in this paper. I obviously have no time to discuss this in any detail, but there's two strategies. They both exploit this idea that the model for the first duration is essentially a single spell mixed hitting time model. So I can immediately apply the results from before, with the complication is that the threshold is the minimum of two thresholds. Once you have that, you can identify, you can use the structure to identify the unobserved heterogeneity, either through variation with the covariates, which is the standard way in this literature, this duration literature, or by making functional form assumptions. Now, again, if you have certified data, this can actually be done without many assumptions. And then you can use now I've only used the first exit, then you can use data on the second exit in a selected sample, namely those markets where you see sequential exits. But selection is not a problem anymore because I've already identified the unobserved heterogeneity to actually learn about the payoffs in the lone state, okay? And then once you have those primitives, so what you identify is the mu and the sigma and the other parameters of the Levy process, plus the reduced form decision rules. So now that means basically that, for instance, in this example, you already know the lambda and the psi, right? Now the question is, if I know the decision rules, the thresholds in this case, what can I learn about the other parameters? Now clearly you need to say something more than just this, right? Because you need, for instance, say, well, there's only heterogeneity in C or something like that. Otherwise, you cannot separate the heterogeneity in C and R. But you can see how you can actually build up the identification argument from that. So we have another approach as well. So I will skip that. And I'm almost done. So there's maybe one more minute. Yeah. One thing we're still working on a bit is estimation. So estimation for a parametric case with and work in duration analysis is often flexibly parametric. Flexible functional forms that can be scaled up with parametric. Now that would be very easy in a two-player case. It's very easy, and we actually do so, to write down the likelihood for potentially censored data And in the Brownian motion case, you know what these first hitting time distributions are, the inverse Gaussian distribution. So the model is basically a multivariate mixed inverse Gaussian model. So you can easily do that. But of course, in general, it's harder, right? So in general, if you have general Levy processes and more than 2 players, it's not so clear that you can do that. And so we develop both simulated likelihood and simulated method of moment methods in the paper, and they turn out the simulated likelihood methods works for a small number of players, and the method of simulated moments, for instance, we tested on an application of the size of the union armament defection, and it also works very well. So with 100 players, it still works pretty well. So that estimation is not a big deal. And the idea of this paper is that it offers a proof of concept that you can use these results and methods from the duration literature and apply them to a theoretically important class of optimal stopping problems, the kind of real option style, optimal investment timing style, optimal stopping problem. And here we do that for synchronization games. You can easily imagine other solution concepts and other types of games. So for instance, cooperative problems will be interesting to study. And you can easily imagine that also there you get threshold rules, so you can apply the same results. But you can also apply it to something like a war of attrition, where the strategic substitutes, although there you get some additional complications, for instance, that you need to allow for mixing if you want to ensure that equilibria exist. So it gets a bit more complicated because you get an additional source of randomness in your sample that you would have to deal with, but it's conceptually not impossible. And so that's it. Thank you for your patience.
Okay, great, thanks. Yeah, if we have time for 1 or 2 quick questions while we're changing over here, John.
Another example is in the neuroscience literature, they have these things called drift diffusion models where you think about them as utility processes, correlated Brownian motions, and when they hit a boundary, it's one decision or another, and you can derive, for instance, random utility models, and also the time to decision as joint outcome variables in that framework.
And is it just a different way of modeling the payoffs through a diffusion instead of
Basically, stochasticity is due to neural noise as you're making decision inside.
Okay, it's more like a behavioral
model of this discrete choice along with the time to decision, which you often observe in laboratory experiments.
Mm-hmm. You have to look into that. So
I'll send you.
Yeah, that would be great. Thanks.